Okay, so we're starting on chapter 8. I want to talk about the first part. So chapter 8 actually consists of three parts. Okay. The first will be stress strain and Young's modulus. And then you have the second part of heat conduction. And then the last part would be on heat expansion. Okay, so the first part of this video is going to be on stress and strain and Young's modulus. Okay, so we begin by asking ourselves, okay, if I have some material of some length, right, and then I apply some force onto it, I can either push it in towards itself or I can pull it out, right? One way or another, experience tells us that there's going to be some deformation, some changes in the length. So if I initially push it in, it will get shorter, right? It will get shorter because it's kind of smushed in, right? So we can measure this. We can measure this. We can consider how much force we are applying onto the cross-sectional area. Okay, and this is what we call a stress. So stress on the material, we use delta as a symbol, is simply the force per unit area. And this will have an SI unit of Newton per meter square. Now, the change in the length, so let's say the initial length is L, and then it shortens by delta L, This is what we call strain. Okay, so strain is simply, use epsilon, is simply the change in the length divided by the original length. Okay, and it has an SI unit of nothing because this is in meters and this is in meters as well. So strain is going to be unitless. Okay, all right. So now how do I relate between the amount of force I'm applying it and the deformation, the measurement of deformation? Well, this is where Young's modulus comes in. Which is simply just the stress over strain. It is some constant that relates between stress and strain. And this Young's modulus will depend on the material, density, and so on and so forth. And as you can see here, the stress is again has units of newtons per meter square, and then the strain is going to be unitless. So then my Young's modulus will have the SI unit of Newton per meter square. Okay, so that is just for the calculation part, but of course we can extend this. To talk about the strain energy. Okay, so the strain energy we can apply it onto the stress strain graph or the force elongation graph. But before I talk about that, I'll have to talk about the graphs. Okay, so in the next part of this video, we'll talk about graphs. Okay, so moving on to the graphs related to this topic, we have two graphs that we want to consider, which is the stress strain graph, and then we have the force extension graph. Okay, a few characteristics when you apply. So this is what happens when you apply more and more, sort of stress, or you make more and more extension onto a material by force. By force meaning either you push or pull. As you pull and you extend the object. So let's look at both graphs at the same time. Okay, so as you pull the object, there's a region of the graph, of both graphs, where we call it the Hookean limit. Okay. Generally, Hookean limit will be around just before the elastic limit. Okay, going to be there. Okay, so what happens in this Hookean limit? What happens is that Hooke's law is obeyed. F equals to negative kx. F equals to negative kx. That means in the Hookean limit, it obeys Hooke's law. Hooke's law. Okay. Now, if you keep on pulling, what happens then? All right. Well, before you reach the limit, this is what we call the elastic deformation. So it happens, it deforms elastically. Why do we say elastically? Because it can return back to its original dimensions. Okay, that's why we call it the elastic region. But once you reach the elastic region, then you have what we call plastic deformation. So here we have plastic deformation. So beyond this is plastic. Why we call it plastic? Because it will not return back. So plastic, not return back. Not return back. Okay, it will not return back. This region is just plastic. And then from experience, if you keep on pulling, let's say on a strip or a rod, if you keep on pulling, eventually what you'll observe is what we call necking. It looks like a neck. It'd be very, very, very thin in the middle. This process is what we call necking. All right, so necking. And then of course, eventually, if you keep on pulling it, you will end up with a fracture. Okay, so that strain hardening just means that it's harder to pull. Every increment of force that you pull, right, or that you apply, every increment, you will actually only extend it by less of a less value. Okay, so for example, in the Hookean limit, you might have 1 centimeter change with a 1 Newton force, but in the strain hardening, you might only get 0.5 centimeter change in length when you apply 1 Newton of force. That's what strain hardening means. You just have a hardening of the object, and once it reaches the ultimate strength limit, which is the ultimate strength limit, then you start having necking. Okay, so the peak of the stress strain graph, is actually the ultimate strength. Okay, so if you have a long plastic deformation, this material is called ductile. Long plastic, long or big, large area of plastic deformation. We have a material that is what we call ductile. But if we have a very short or small plastic deformation region, then we call this material to be brittle. In other words, in brittle materials, you don't really see necking happening. And this is true. If you were to just pull on sort of, for example, something that is brittle, so let's clump up some clay and then just pull it apart, you won't really see it stretching out unless you add some water, right? So plastic deformation is mainly when you have a large when you have a ductile material. Now, the thing about these graphs is that you can figure out a few things. one of the things that you can figure out, right, is that, let me just copy that graph. Okay, there we go. So one of the things that you can observe is that, of course, Newton's law, I'm sorry, Hooke's law still applies for the force extension graph, and you have the strain energy to still be half Fx. So you still have here Fx, but of course x here refers to extension, and therefore you have F delta L. On the other hand, for the stress strain graph, you can still figure out the strain energy, right? But it takes a bit more tweaking, and I'll just show you the result. Mainly when you talk about stress strain graph, you don't really talk about strain energy. You talk about strain energy per unit volume. So that's going to be U over V. And then that is just going to be equal to my half stress times strain. And again, a clue to this is that my volume is actually equal to area times length, and then my strain is actually delta L over L. Okay, you can work it out. You can show that strain energy, when you apply it, and then divided by the volume, you will actually get stress over strain. Sorry, stress and strain. Stress multiplied by strain. Okay, so that is the end of the first part, which is going to be on Young's modulus. We have defined what is stress, we have defined what is strain, and we talk about Young's modulus, and then we talk about the graphs. We have two main graphs, stress strain and force extension graph. Okay, and then of course we have characterized the types of material, or at least our description of it, depending on its how big its plastic deformation is. And then of course, last but not least, we've talked about strain energy being calculated from both these graphs. Okay, so in the next part, we'll talk about heat conduction. Okay, so now we're going to talk about heat conduction. Generally, we want a law that relates between, so let's say you have a material and you heat one end of it to some hot temperature, and then you have you maintain a cold temperature on the other side, then you know that the warm part over here, and then the cold part over here, eventually the warm part will sort of propagate to the cold part, and then they will reach some level of equilibrium. But of course, this is long way to go, so we need to know how fast is that heat energy moving. So to dictate, or at least to quantify this heat energy transfer, we look at Fourier's law. So Fourier's law specifically in one dimension. This is so in your syllabus, you talk about one dimension. You don't really talk about 2 or 3 dimensions. You only talk about one dimension. So let's look at what Fourier's law says. Fourier's law says that the heat energy flow, the rate of heat energy flow, dq over dt, is actually dependent on a few things. It depends on how big of an area you have, so the cross-section area, and then it depends on the material, so kx, the coefficient of thermal conduction, okay, the coefficient of thermal conduction in x direction, x being just the one choice of heat flow, and also it also depends on the temperature gradient of this being, of course, I'm choosing x to be this direction generally. So this is what Fourier law tells us, which is it depends on how big of an area you have. It depends on thermal coefficient, thermal coefficient, thermal conductivity coefficient, and then it depends on the temperature gradient. That's all it means. That's all it depends on. So now what we want to look at is a graph. If we graph it out, if we graph out the temperature, so let's say you have a graph here, and then I'm just going to draw let's say a simple object. Now this one is in reverse. I have my cold side over here, and then my hot side over here. And we are talking about what is the temperature at a single point. If I draw out a single point, I can figure out its temperature. Now, for an insulated rod, we have a nice graph. We have an uniform drop in temperature. So for an insulated for insulated rod, I have a uniform drop in temperature. When I say insulated, I meant it is insulated by some other material that is a poor poor conductor, poor thermal conductor. So insulated by a poor heat conductor. Okay. Now, on the other hand, if I have a non-insulated rod, so I can extend that graph. To keep on going down. I can see that the temperature drops much faster, and the reason for this is because heat is lost to the environment if it is not insulated. So heat loss to surrounding if not insulated. Okay. I want to make a key point here. If you actually have two materials, so let's say, and this is a very common question to ask, if you have two different materials, and then let's call this, you have temperature 1, this is the hot side, and then you have temperature 3 at the end, or temperature 3, and then you have temperature 2 in the middle at the interface. Let's say you have material with K1 and K2. Then in general, you can apply steady state, where you have dq1 over dt is equals to dq2 over dt. This is what you can apply to figure out the temperature. Okay, so the negatives cancels out, so that's nice. And then you assume that their cross-sectional area is the same. This is generally the approach to problems like this. You will have kappa 1 a dt over dx equals to kappa 2 a dt over dx again. Now, of course, dt is just the cold side minus the hot side. So then I'll have kappa 1 dt is T2 minus T1 over, so let's use, this is x1, x2, x3. Then I'll have x2 minus x1 equal to kappa 2 T3 minus T2 over x3 minus x2. Now, what I want you to notice in this particular equation is that I have T2 in front for one of the equation, and then I have T2 on the other side, because it is always hot minus cold, hot minus cold, cold minus hot, cold minus hot. Of course, you'll have a negative sign somewhere here, but they will cancel out on both sides. So it's the most important part is actually just the fact that it is steady state. If you have a combination of materials, then you will have what we call steady state, where the rate of heat energy is going to be the same. That's the most important part. Okay, so in the next part of the video, I'm going to talk about heat expansion. Okay, so this is the third part of the video. I want to talk about heat expansion. In general, when you heat things up, they will expand. And now we want to quantify that. We want to quantify heat expansion. Unlike the heat conduction, we want to consider 3 dimensions. Okay, now of course, this is referring to a very small small change in temperature, not that large. You don't go from 0 to 1,000 degrees. You generally probably would go from 20 to 35, 20 to 50, something like that. But in general, we will start at 20. And there's a reason for that. There's a reason for why we start at 20 and why we assume that it's going to be a very small temperature change. Okay, so first things first, let's consider in one dimension. Let's consider in one dimension. If you were to heat something up, what you will find is that the change in length, because we're talking about the one dimension, so we're going to talk about length, is going to be equal to my alpha times my original length. My original length, let's call that L naught, and then times my change in temperature. Okay, that's what you'll have. Now, of course, I can expand this. I can expand on this, where you have the change of length is just L final minus L initial or L original, right? I can rearrange this to have my final length to be equal to my L naught 1 plus alpha L naught, sorry, no longer L naught, alpha delta T. Now, some of you might be asking, what is this alpha? This alpha is just a coefficient, and this is a coefficient of thermal expansion, Now, of course, because this is a linear case, let's call that coefficient of linear thermal expansion. Okay. Now, if we were to move on to 2 dimensions, you no longer talk about length. I want you to imagine a square of length L times L. Then you'll have to talk about expansion in both directions. So both to the right, both in the x-axis and the y-axis. So what you want to do instead, what you want to do instead is to find the final area, which is just going to be the length final and then squared. This length final squared, I can of course take it from the one-dimensional case, which gives me just the length original squared times 1 plus alpha delta T squared. If I just square that, I'm left with, so let's see, I'll have L naught squared, I have 1 square plus 2 alpha delta T plus alpha delta T squared. Okay, now going back to what I said earlier, right, which is that the delta T is small, small delta T. If it's a very, very small change, then I can ignore its square value. So what that means is that my AF is simply L naught square 1 plus 2 alpha delta T. Okay, so this goes away. So this one goes away. Okay. Again, L naught here is just A naught, right? The original area. And this is what I have as a final equation. But of course, I can make things a bit easier for me by substituting or just having one coefficient. This is a constant by the end of it. So I can have 1 plus beta delta T. So where beta is equal to 2 alpha. So what is this alpha? This alpha depends on materials, depends on many factors, but generally it is different for every material. So when you do questions, generally the question will provide you with a value for alpha or beta. Okay, but of course this value generally is given, this value alpha is given in approximately 20 degrees Celsius. So this delta T cannot go very far away from 20 degrees Celsius. Okay, so last but not least, we want to talk about what happens if it's a 3D situation. So if you imagine a cube of sides L, L, and L, then you can have volume equals to length cube. Okay, so final length cube. And then you can do the same procedure that we've done before, but of course, if we ignore, or at least if we neglect delta t square, we'll definitely neglect delta t cube. Okay, and what you'll get from here is that the volume, final volume, is equals to original volume and then 1 plus gamma delta t. I went squares and I got 2 in the earlier case. I went squares and I got 2. So if I will go to cube, there's a high chance I'll get 3 alpha instead. Okay, so that is on thermal expansion. And that summarizes our session or our video on chapter 8. We've talked about, let me see, we've talked about Young's modulus, we've talked about heat conduction, and last but not least, we've talked about thermal expansion. So, sorry, thermal expansion over here. Okay, all right, so I'll see you in the next video.